So, welcome to module 4. That we have understood something about security and different functionalities of the operating system, certain services that the operating system need to take care, and we concluded last module with security issues. We distinguished between protection and security, and in this module we will talk more about OS security issues. Please understand that this course is essentially server and a network administration course for security engineers. So, we will emphasize more on the security aspects of operating system. So, typically how does an operating system protect itself? So, the operating system will basically give two modes of execution, what we call as a dual mode. In a dual mode, there is something called a user mode, in which the user process, the application software will do some activities, right. So, and basically in the user mode, a process which is a program in execution, when it is executing in the user mode, will have restricted privileges. It cannot go and touch certain parts of the operating system, or it cannot go and touch certain part of the memory. So, it cannot go and change certain values. And there is another mode which we call as the kernel mode, wherein from the user mode we basically execute a system call and come to kernel mode. In the kernel mode there is more privilege. So, then certain parts of the operating system can be checked up. So, the operating system, so it will be in two modes of execution. When a user process starts executing, then it will be in the user mode. So, that user process cannot come and touch anything within the operating system, right. And when certain important operations have to be taken which are very close to the hardware, then there is a switch into the kernel mode, and in the kernel mode certain operations can happen. For example, let us take a very simple hello world program. Some part of the program, say there is a printf statement, there are other statements other than the printf, all those things are basically executed in the user mode. And when I do a printf, then there is a system call basically which will go and touch the device driver of the monitor and the graphics adapter, and then the hello world will go and print there, and that part is basically a kernel mode. So, when a process executes, some part of it will be executed in the user mode, and whenever it does a system call, we go to a kernel mode and starts executing in the kernel mode. So, to distinguish between these two modes, let us look at supervisor/kernel mode, where one can execute all machine instructions, one can reference all memory locations, and there is a user mode where only a subset of the instructions can be executed and only a subset of memory locations can be accessed. So, if we go back to the information security 2 course on architectural 8 information security, there we have introduced 4 privilege levels or 4 modes, privilege 0, 1, 2 and 3 in the context of the x86 architecture, and we have explained how this type of intra-process protection can happen and how you switch from one mode to another mode. There is a dedicated assignment on task switching which basically talks about how we can go from 0 to 1 to 2 to 3 and back 3 to 1 0, and how one can be at a level 3, that is probably the user mode, and go and execute a program that is level 1. How are interrupts handled? So, are the interrupts are in user mode or are they in kernel mode? Can I execute an interrupt service routine in the user mode? Can I execute it at a kernel mode? All these answers are available in our architectural 8 to information security 2 course. I urge the readers to please look at the assignments specifically with respect to what we call as task switching in that course. So, just to give a glimpse of what we covered in that course, there is a notion of a kernel, there is a notion of a memory. So, what do you mean a notion of a memory for a kernel? So, the memory essentially is basically split into two parts. One part is for the user space, another part is for the supervisor space. Or so, when the kernel is executing, it can access the entire memory, namely a user space and the supervisor space. But when a user process is executing, it can handle only the user space. And so, the supervisor process will work in the supervisor mode, the user process will work in the user mode. There are instructions, for example, if you go back to the information security 2 course, there are instructions like int, int etc., which are like lgdt, LLDT, load global descriptor table, load local descriptor table, many important instructions that are all what we call as privileged instructions. Those can be executed only in the supervisor mode, it cannot be executed in the kernel mode. And we could go and reserve memory. Every byte of the memory can be given a privilege level. So if a memory location has been given a supervisor level privilege, then the user process cannot access it. So these are some of the very interesting things that form the basis of protection and security in the operating system context. And then there are lot of care that is taken while there is a switch from a user to kernel mode. One important care is that I ask for certain kernel functionality, and what happens, it goes into the kernel mode and never returns back. There is something that has happened there, and the system call does not happen. So one of the things that many operating systems, specifically real time operating system, does is when we go from the user mode to the kernel mode, they go and set up what we call as counter, and you set up some time quantum in the counter, and when the counter reaches 0, immediately it generates an interrupt. This can also happen from a user process to a kernel, and also it can happen from a kernel to a user process. So as an operating system, I start executing a user process, and then what happens is that I need to have a response from the system, and if the system goes on to an infinite loop, then I want to pull it out after some time. Then I actually set a timer, and based on the timer interrupt, I pull it out. This is the basis of round robin scheduling. The other part is that when I am looking at a real time processing, and there is a user process which is requesting some service and it does not come within some time, I can still have a timer which kicks it back. It may not take it back to the user process, but it can take it back to the another OS routine which can do some file safe type of activities. So there is a notion of an hardware timer which is very, very important in the context of operating systems, which can basically be programmed to get quick responses, to ensure that responses are quick, and in cases the response is not quick, then it can take some remedial actions to see that no major damage is done because of the lack of response. So to look at in a nutshell, if you look at an operating system, it gives, there is an underlying hardware, and that hardware has different things that it do. The hardware has the IO devices, it stores files, it needs to be secure, it needs to be audited, there are multiple resources that needs to be managed, there are a lot of error that need to be managed, IO devices are there. So what does the operating system do? It actually provides services to other part of software that resides on the computer through what you call as a system call. So there is a user program, the entire setup is to basically run that user program properly, and the operating system provides an user interface using which the user program can call the system calls. And what does the system call do? It actually provides an abstraction of the hardware resource available. And what are all the abstractions that you see? I can look at mechanisms by which I could control the program, there are IO devices, I see a file system, there are communications that could be established, error management, resource management, auditing, security, everything are the abstractions, and the system calls can be used to basically go and achieve these abstractions. Namely, I want to control a program, I use a system call to go and control the program. For example, in Unix, fork is a very, very interesting program control mechanism which is basically a system call. So to sum up, the operating system provides facility for program creation and execution, it gives you access to IO and files, it provides system access, it also provides lot of resilience in terms of error detection and response, it is responsible for allocating resources that a process, a program and execution wants. It is also very important for us to account in many of the systems which are paid systems where you pay for a service, there is an accountability, and then there are, for legal reasons we need to know who has accessed the system, so there is logging that needs to be done, which is also under the head of accounting. Operating system is also responsible for program execution, for IO operations, for file system manipulation, and also communication between the processes within a particular system or across systems in the case of a network distributed operating system end. These are all some of the services which the operating system provides, for which we have understood to some level so far. In addition, the operating system should have error detection, it should have additional functions exist not for just helping the user, but rather for ensuring efficient system operations. For example, thermal management today is a very, very interesting example of additional functionality. When a chip heats up, then automatically some of the CPU cores. So, if you have a multi-core system, some of the cores are put into sleep, and then resource allocation, as we have seen, accounting, protection, etc. So, these are all some of the services that the operating system provides. Now, how do we request for the services? There are two ways by which one can request for the services. In many of the operating systems today, it is basically done through system calls. What are system calls? It's basically a process. When it is executing, it needs to get some service from the operating system. It executes a trap, and the moment I execute a trap, we go into an operating system interrupt handler. As I told you, every trap will have a number. We go to an interrupt table, and that particular interrupt service routine starts executing. And after that interrupt service is over, we come back to the application. So, this is a notion of a system call. There is also something called message passing. What do you mean by message passing? The user actually constructs a message which it wants to deliver to the operating system, and it invokes a send to pass the message to the OS, and once it sends the message to the OS, it gets blocked. It starts waiting. So, some other process can start working, and then the OS actually from its end it receives the message from this block, then it executes some functions, and after the function is completed, returns back a message. Now, the process which is blocked again gets unblocked and starts executing. So, this is another way of getting a service done from the operating system. So, one is called the message passing, another is called system calls. So, this basically graphically teaches you what is the difference between a system call. System call is nothing but a call of some nature which creates a trap which goes as an interrupt, and you return from that. In a message passing interface which we call as MPI, we send a data from a user process to a kernel process. The kernel process receives the data. After finishing some computing, it sends back an answer, and which is received by the system call, and immediately it starts executing. So, these are two ways by which one can get operations done out of an operating system. So, what are system calls? System calls basically are, as I told you, like printf, scanf, etc. malloc is an example of a system call, allocate memory, and there are whatever you see on the libraries of the stdlib or stdio, these are all basically system calls. And when we do a system call, essentially we need to give some parameters. For example, if I want to do a scanf, please understand I have to give the address to which I need to scan in the data. When I want to printf, I need to give the value. So, there are some parameters that are passed between the user process and the corresponding system call, and that basically happens. There are many ways by which one can pass the parameters. One can pass it through the stack, one can pass it through specific memory locations, one can even pass it through registers. So, depending upon the type of things that we pass, depending upon the mechanism that is decided, user process can pass parameters as a part of the system call. So, it is like any other one subroutine passing parameter to some other subroutine. The same process can be there, but with lot of security here, right. So, in the information security 2 course, please understand that we had covered in depth about how data is passed between a privilege level 1 code and a privilege level 0 code. There are different stacks that are involved, and why do we need multiple stacks? All these things have been explained very in detail in the information security 2 course, which would be of very high importance when you want to appreciate how parameters are passed between an user process and the corresponding supervisor process. Now, if you take some of the old operating systems like MS-DOS, so all the levels, namely the application programming and the resident system programming, MS-DOS drivers, everybody directly talks to the device drivers. They actually talk directly. Every layer can touch the hardware, bypassing the intermediate layers, as you see in this particular thing on your left hand side. So, but on a hierarchical structure like Unix, where you have a layered operating system, so there are different layers as you see here. There is the undermost layer is terminal controllers and terminals, device controllers, device memory controller. These are all the hardware. On just top of that hardware, as you see, there are kernel interface to the hardware, and then this is the operating system there, where you have signals and terminals handling character IO stream and IO system and terminal drivers, file system, and then CPU scheduling, page replacement, etc. So, that is the operating system. Then there is a system call interface on top of it, and then you see there are shells and commands and compilers, and then of course the last one is the users. So you see at least there are 4 layers that we are looking for. And perhaps that's the reason why maybe that's the reason why the x86 architecture are 4 privilege levels. So all the any OS like Linux, Windows, Vista will follow this hierarchical structures and it has 2 important separable parts: the system, which is the space / program, the kernel space, which is again the space program. So the kernel, as you see in the slide, comprises the system call interface and the kernel interface, and then we have all the file system, CPU scheduling, memory management, all these modules, they form the kernel there. So this leads us to what we call as a layered operating system, which I have been talking of. So we have layer 0, which is the highest privilege and which is very close to the hardware. Then top of it layer 1 with lesser privilege, and go on. I can go up to layer n. So, but the bigger difficulty here is how do we define which part of the operating system goes to which layer, and what sort of capabilities an user will have on each of these layers. And so sometimes this definition of a generation of this layered operating system tend to be less sufficient, because if a layer n code wants to execute on the hardware, it may have to pass through layer n-1 to layer 1. So there could be a lot of system calls and stuff like that, and lot more of before a program can touch the hardware, there could be several other programs which execute on the same hardware to enable this to go and access that hardware, and that causes this efficiency loss. One of the interesting things that has come up in the recent time is this microkernel based OS structure. So I have a kernel, I take that kernel and lot of things that are very close to the user space, we push it into the user space, and essentially then what remains is a very small part of this kernel which we call as the microkernel. Now the microkernel, so since all the other parts have been pushed, the microkernel actually becomes much smaller, and it becomes easy for us to port it across multiple architectures. And it is also very much possible that I can go and do certain formal verification of these microkernels, because it is all very small in size, and I can ensure that not only that the desired functionality is executed by the microkernel, but functionality that we do not desire, that will not be executed. This answering to this second question is very difficult. Will the software execute what it is supposed to do? The answer could be easily done. We can give an answer for that easily. Will the software, can you ensure that the software will not do what it is not supposed to do? That is a very difficult question to answer, because we do not know what it is not supposed to do. I know what it is supposed to do, but I do not know what it is not supposed to do. And so for answering that type of question, a more formal approach is necessary. And if I have a huge kernel, I can't do any formal approach or formal verification on it. If I have a microkernel, then one can do a formal verification on that, and that makes the notion of a microkernel very, very important in the context of building secure operating system. So today, if you look at an operating system, there are multiple modules. As you see on the slide, you have at least 7 modules, one for scheduling, one for file system, another for system calls which you can load, some we can say I could have executable formats, I could have streams, I could have other miscellaneous modules. So what is the interesting thing about this modular operating system? I can go and load some module as I need. Suppose I do not want some devices or thing, I will not go and load the drivers at all. Right? If I do not want to support certain system calls, I need not load those system calls. So I can build up a new core of say, for example, this is quite true, Solaris was the operating system in the past, which basically gave the notion of a modular OS structure in a very big way. So the thing is that I need not load certain modules. For example, I want to disable USB, we can go and say do not even load the system, the driver or anything related to USB, just do not compile your kernel by removing all those things. That makes your kernel extremely secure. That can give you a much more guarantee that somebody can't break open by the traditional means to get information out of your system. So a modular OS structure is extremely important towards building up a secure OS. The last thing that we will cover today is about in this module is about virtual machine. What is a virtual machine? Virtual machine is nothing but a software box, and many such box could exist on a single hardware. What you see in, so what normally we see is that in a normal machine there is an hardware which you see on your extreme left in your screen. There is a hardware, then there is a kernel, and that kernel is executing on the hardware, and there will be processes that are executing on that kernel and which will be utilizing the hardware through the kernel interface. So this is, so there is only one operating system, and this hardware is dedicated to this operating system. Now you see what is there on figure B, that is on your middle of this slide. Now you see there is a single hardware, then there is a virtual machine implementation, like there are multiple virtual machines. KVM is a freely available virtual machine today. You implement the virtual machine layer, and what will that virtual machine layer give you? It will give you what you call as boxes, virtual boxes, which we call as VM1, VM2, VM3. I can create n such boxes, and on each one of this box I can run a different operating system. So the kernel on VM1 can be Windows, kernel on VM2 can be Linux, etc., etc. So I can run multiple operating systems on this, and in each of these operating systems I can run processes. So now the processes corresponding to VM1 thinks that the entire hardware is dedicated to it. Processes corresponding VM2 thinks that the entire hardware is dedicated to it. It will not even know that VM1 exists. Similarly, VM3 thinks all the processes there will think that the hardware is dedicated to it. It may not know that VM2 exists, or it may not know that VM1 exists. All the processes in VM1 will execute in isolation, isolated from the processes of VM2 and VM3. Similarly, VM2 processes will be isolated from VM1, VM3, and VM3 processes will be isolated from VM1 and VM2. This is the notion of a virtualization, and this is supposed to, in practice also, improves the hardware utilization. Now one of the important thing that comes out of this is, now again I am sharing resources, so there should not be, the isolation that I talked should be perfect isolation, should be provable isolation, such that a process in VM2 should not be in a position to go and leak information about generated or used by process in VM1. So there should be a complete proved isolation between these VMs which are executing on the same hardware. The real challenge here is that all the hardware resources are shared between VM1, VM2 and VM3, right? And with that sharing we need to ensure that there is no information leakage, which makes the whole thing a very complex affair. So that's what we have mentioned here. So today virtual machines are very, very important today. What they form, almost every data center in the world would have at least one installation of a virtual machine. Virtual machines not only gives the notion of a more efficient hardware utilization, it also helps in what we call as consolidation of applications or consolidation of your server, and that way virtual machines are going to be extremely crucial in days to come. With this we complete this module 4. We will talk more about operating system from the process and file management in great detail in the next module. Thank you.